to the actual positron in relation to mu.
If you can make sure your mic's on, that'd be great.
So, we're going to study this process. It is definitely the simplest QED process. It is used in particle accelerators mostly for calibration because it's very clean theoretically and easy to measure also. So it's one of the examples where we can make a clear theoretical description of this process. And basically, this is because muons and the electrons, they never interact strongly. So perturbation theory for this process works very well. And we'll study it to the leading order in perturbation theory in QED. So what is the situation that we'll consider? Well, there are two electrons that collide and head-on. So we'll consider this process in the center of mass frame, imagining two beams of electrons and positrons colliding. And then, so in the collision, they can produce all sort of junk. And in particular, they can produce a pair of muons, so, which can fly well, in some direction that makes an angle theta with the original incident electron beams. Well, muons are they are twin brothers of electrons, so the only difference is their mass. So they're heavier. The mass of the muon is 106 MeV, and I remind you that the mass of the electron is 0.5 MeV. So they are quite a bit heavier than electrons. Yes.
At some points that sometimes you're drawing Feynman diagrams and sometimes you're drawing just illustrations of portions. How do we tell the difference?
So this is the illustration. There should be no angles in Feynman diagrams, right? So it's just there is no vertex of direct interaction of electrons and muons. So the only important interactions, I mean, here for our description of this process are electromagnetic interactions, and electrons and muons participate in them in absolutely the same way. So the Lagrangian that we can start with is obtained from, well, this is the QED Lagrangian, but instead of one set of fermions, we have two, electrons and muons, and they interact with the A in the same way and with the same strength. So muons have the same electric charge. Okay, so all right. So we let's first discuss kinematics a little bit. So for electrons, well, their four momenta are obviously, well, their energy and they move with some momentum. With absolute value we know, so it's related to energy by the usual relativistic dispersion relation. And let's call this momentum P prime. So in the center of mass frame, the momenta, the three momenta of electrons are opposite and equal in magnitude. So what about muons? I claim that muons will have the same energy. This is easy to understand because, okay, so after electrons and positrons have annihilated, all of their energy and momentum is transferred to the muons, and in total they have zero momentum. So muons will also fly apart with the same with momenta that are the same in magnitude, and therefore they will have the same energy. So the energy is equally distributed between muon and anti-muon. And since the amount of energy is the same after and before the collision, then they will have the energy of the original electron. However, their three momentum will be quite a bit smaller because they have more mass. So the kinetic energy, they have bigger rest mass energy, so the kinetic energy will be smaller. Right, so this is just kinematics. And now what we want to do is we want to calculate the cross-section of this reaction. Before going into the details of the QED calculation, let's do some rough estimates. What do we expect to get? So first of all, the cross-section will be small because of interaction strength is small. We can estimate how small it will be because, let's see, so this is will be the process that appears at order e squared. Right, so the electrons and positrons will annihilate into a photon. So this will give us a factor of E, and then this photon will produce the muon pair. So that gives another factor of E. So the amplitude will be proportional to E squared or to alpha. The cross-section is the probability, it's the square of amplitude, so it will be proportional to alpha squared. So we know from the start that the cross-section will contain a factor of alpha squared. But then the cross-section is dimension full quantity. It has dimension -2 in the units of energy. It's the area after all. So we have to make it, it should scale with the energies of masses of the particles involved. So let's do the dimensional analysis. So what dimensionful quantities do we have? Or and what quantities characterize this process? Well, there are three of them: energy and the masses of the particles that are involved in the process. But now you see that the energy, so first of all, this process will have a threshold. So electrons should have enough energy to produce at least the energy should be at least as big as twice the rest energy of muons. If it's smaller, well, then muons cannot be possibly produced. So the reaction will only go starting from some threshold energy. Okay, And so the energy, therefore, must be bigger than the rest mass of the muon. So the rest mass energy is twice the energy of each of the particles. It will be bigger than 100.106 MeV. And then you see that the mass of the muon is much bigger than the mass of the electron. So since, well, the electron mass by dimensional counting can only appear in combination with mu or with energy, the correction will be very small. So the corrections due to electron mass so they will be of order me squared divided by m mu squared. So this is something of order 10 to the minus 5, I think. So they're very, very small. And to the first approximation, we can neglect them. In fact, corrections of the next order of perturbation theory would be of order alpha. And so they will be of order 10 to the minus 2. So they will be much bigger than corrections due to electron mass. So keeping electron mass would have been a wrong mistake because, okay, there are effects that are more important. So all in all, this means that we can just set m electron to 0. So we can consider electrons as massless. And this is because to produce muons, we have to collide them with quite a big energy. So we simply set me to 0. So this will simplify things quite a bit. And this leaves us with two parameters of dimension of energy, the muon mass and the center of mass energy. So the cross-section will be a function of those two. So dimensional analysis then tells us that the cross-section will be proportional to alpha squared. Then dimensional analysis tells us that it should go as 1 over energy squared. And then there can be some function of the muon mass, but it has to be normalized to the center of mass energy. So we cannot tell anything more just on account of dimensional analysis. But we can certainly say that if energy is much larger than the muon mass, well, this means that we just set this ratio to 0. And so then at large energies, the cross-section will decrease as 1 over energy squared. So we can also estimate what happens when energy is very close to threshold. Well, then we can invoke the following argument. So if you recall the formula for the cross section, it has two ingredients. So it has the matrix element squared times the integral over the phase space. And so near the threshold, the phase space shrinks. It has a very small volume, right? So it's the reason why there is a threshold is that the phase space shrinks, and when we reach the point where particles can no longer be produced, the phase space goes to 0. So near threshold, therefore, if nothing specific happens to the matrix element, the behavior of the cross-section will be determined just by phase space. And so we can write that there the behavior should be simply proportional to the phase space. And so this the phase space shrinks as the square root. So we expect a behavior like that with some constant that we cannot determine before doing the honest calculation. So simple as they are, these arguments more or less determine how the cross-section will look like. So if we plot it against the energy, there will be a threshold at energy equal to the muon mass. So where the cross-section will turn to 0 as a square root. And then we know that it goes to 0 at infinity as 1 over a squared. So that's, we can just tell from dimensional analysis. Yes?
I think I follow your argument about why the energy is just barely big enough, then the cross-section behaves according to the volume of phase space as opposed to according to the amplitude. But why should the dependence of sigma on how the phase space, its size, look like that?
Well, that follows from the formula that we derived on the last lecture. So it's the phase space, if you remember, was proportional to ratio of particle momentum to the particle's mass for the two-particle phase space, and that's actually the kinetic energy. E over E is the velocity of it's the square root of the kinetic energy. It's particle's velocity, right? And this is precisely what's written here. So that's E minus m. In the non-relativistic case, this is mv squared divided by 2. So this is just the velocity of the produced muons. So the cross-section should go as linearly with their velocity when they are produced almost at rest or in non-relativistic sort of state. All right. So therefore, we know the cross-section in the two limits, or at least we can understand its dependence on energy. So since it should be a continuous curve, there should be a maximum somewhere. And then it should decay very fast with the energy. So this is the curve that we expect to obtain. Now let's calculate its shape just exactly. In particular, these simple dimensional arguments don't tell us anything about the angular distribution of muons, and I don't have any good qualitative explanation for that. So to understand it, we need to do the calculation. So to do the calculation, the first step is to draw the Feynman diagrams. And the nice feature of this process, which sets it apart from all other QED processes, is that there is just one diagram, which is, well, easy to understand. So we have incoming electron, an outgoing positron. So they annihilate into a photon, which then produce a muon-antimuon pair. This would be minus, plus, mu minus, plus, and they have the kinematics is over there. Now, right. So, if you remember when we studied the scattering of electrons on positrons, there was also this diagram, but there was also in addition we had a diagram where electron was passing through the whole from left to right, and so this diagram was not important there because it was suppressed. Now here, the second diagram is simply impossible because electrons and muons are different particles. So electron cannot become, there is no vertex in the Lagrangian that would make a muon from electron. So the only way for them to communicate is through photons. And so to the leading order, we just have a single diagram. Yes? So the other diagram I mentioned is this one. So for Møller scattering, we would have two diagrams. And then, so the method of Møller scattering will be more complicated mathematically because there will be interference there between these two diagrams. And so instead of, like, you have to compute the probability, you need to take the square, right? So if you take the square of the sum, you have 3 terms, and here you will have just 1. So for that reason, the calculation here is the simplest possible QED calculation one can do. Well, then we need to write down the matrix element for this amplitude. And so what is it? Well, so first of all, this is the second order QED process. So there is a coupling constant squared. And then we need to, well, you see we have only one propagator and 4 external lines. So each external line is associated with the wave function. So the wave function of incoming positron is V bar. Okay, so let's assign spin S prime here. So the incoming electron has the wave function U, and we say that it has spin S and momentum P. And so this has momentum P prime. So then outgoing muon has the wave function U bar R and momentum K. And so this has the wave function V R prime of K prime. So we have to multiply all these wave functions, and each vertex has a factor of gamma. Yes?
Would you mind reminding us why the correction needs to be second order? Second order. Would you mind reminding us why the correction is
It's second order. So each vertex carries a factor of e. So it is the second. This is just part of the vertex. So the vertex is minus e I times the gamma. Yes.
So I think since you draw this diagram, I mean the second diagram, so this is only the case when you have a neutron electron configuration. So did you say that if you want to study the creation of two ions, then this second diagram is impossible because there is no vertex connecting the electron?
Yes. So electron cannot become mu by emitting a photon. So it's just there is no such thing.
So is this diagram the only contribution?
It's the only contribution. So this is just one contribution that one diagram that they have to compute. So any other diagram will have more vertices and therefore will be of higher order in alpha, and so will be very small. Okay, so let's see. So all right. So what we do is we multiply so factors for each fermion line, going from its end to the beginning. So here what we have V bar S prime P prime gamma mu. Let's say that the index here is mu, here is mu. US of P. Then we have the photon propagator, which is minus I G mu nu divided by the momentum flowing through the photon line. So what is this momentum? This is the sum of momenta of electron and a positron. So this will be equal to P plus P prime squared in the propagator. And then we have the wave function factor for the muons. So, okay, so this is the amplitude. What we need to calculate is the amplitude squared. And the amplitude squared will be equal to, well, complex conjugate amplitude times the amplitude itself. So in principle, we need to take complex conjugates of all of the elements here. And so for that, we need to know how to take the complex conjugate of the spinors. For that, we have a nice formula. So if you have a spinor product like that, so we have products of this type. And we want to take complex conjugate of this. So we write it as well, explicitly as the product of spinors and gamma matrices. And so this is by definition is V dagger gamma mu dagger gamma 0 dagger U. So then V dagger is V bar times gamma 0. Gamma mu dagger is gamma 0 gamma mu gamma 0, and gamma 0 dagger is gamma 0. So at the end, this becomes V bar gamma mu U. So we can, the complex conjugation acts in the simplest possible way. Just interchange the spinors with the bar, with the spinors without the bar. So we can write, sorry, this is m squared. So we can write now the square of the matrix element. And so what will it be? It will be e to the 4 then from the photon propagator we'll have p plus p prime raised to the power 4, meaning that it's 4 momentum squared. And then some longish expression involving the spinors. So let's write it explicitly. So this will be v bar s prime of p prime gamma mu us of p. And now I should write the complex conjugate of that, which is u bar s of p gamma gamma nu v s prime of p prime. And then we have times u bar r of k gamma mu v r prime of k prime v bar r prime of k prime gamma nu u r of k. Well, then we have explicit expressions for the spinors appearing here. Yes.
Why can we reorder the factors like that?
Because they are, they're fully contract. The indices are summed over, right? So these are scalar expressions. It's like, right, u bar, then some gamma matrices u is just a number. So for u and v, we have explicit expressions. We can plug them in this formula, and it becomes a mess. It's just very, very long expression. Of course, mathematically you can do it easily, but not on clever. So fortunately, in most interesting, physically most interesting situations, things actually simplify. And this is because, okay, so the amplitude that we computed actually contains, let me count, 4 independent amplitudes, right? Because each of the external particles has a spin. So electrons can have spin up, spin down. Positron has spin up and spin down. And the same for muon. So we computed, 2 to the 4, 16 different amplitudes of various spin states involved in the reaction. But usually, if you think of some experimental setup, well, the beams are typically not polarized, so they contain electrons with various spins, and the total spin should be equal to 0. So the probability to find an electron with spin up is the same as probability to find electron with spin down. So in other words, half of the colliding electrons will have spin up and half will have spin down. And the same is true for muons. So if you want to compute the probability averaged over all possible collisions that happen, then we just need to average over the initial spins. And also, typically the spin of the outgoing muons is not measured. So they just, I don't know, they leave some tracks in the detector, but the tracks don't distinguish muons with up or down spins. So in the experiment, they're counted equally. So the most interesting cross-section then is the one that is spin averaged and is inclusive with respect to spins of the muons. So this means that we want to calculate the sum over initial spins and final spins. But for the initial spins, we introduce a factor of one quarter, right? So we average over electron spin, so meaning that we sum over all possible spins with coefficient 1/2 probability. So we sum the contribution of the amplitude of for electron to have spin up with the coefficient 1/2, right? And then the amplitude for the electron with spin down with coefficient 1/2, the same with the positron. But for muons, we just sum over all spins, right, without any factors, because all of them are detected according to our assumptions. So what we need to compute is this sum. And you see that indices there appear twice each. So we just need to sum over S prime, S, R prime, and R. And this can be done by the formulas that I guess were derived in one of the tutorials. So for instance, we need to compute the sum over S. So let's see where S appears in this formula. So where it appears is an expression like that. So US of P, U bar, S of P. So what it gives is can be written in terms of Dirac matrices. Now there will be also sums of the type VR of K, V bar, let's say R prime of K prime, VR prime of K prime, and that's equal to K prime slash minus M. So at the end, amplitude squared can be written in a reasonably simple form. So first of all, let's replace E by alpha. So E squared alpha is equal to E squared divided by 4 pi. So let's replace E to the 4 by 16 pi squared alpha squared. 1/4 makes it 4 pi squared. And then we need to use these formulas. And so we use them 4 times. And as you see, the two expressions then they are completely independent, that are separated by the cross. And each of them becomes a trace over indices. I don't know if it's visible, but they are multiplied in such a way that the matrix indices are sort of contracted on a circle. So the U's in the middle become P slash plus M. Then we have the gamma matrix. It multiplies V as bar, but V as bar is summed with the V bar that stands first in this expression. So that becomes another combination of gamma matrices. And so what we get is trace of gamma mu. And then we use these formulas. Neglecting them, so the electron mass is neglected. Then we have gamma nu. And then we have P prime slash. So in the second expression, we cannot neglect the mass. So this will be equal to gamma nu K prime minus M mu gamma nu K slash plus M mu. So this is already not that bad. At least we know how to calculate it, because, well, at some point we learned how to take traces of products of Dirac matrices, and finally this we have the use of these formulas, because here we need to compute the trace of 4 gammas. So in general, what we need to calculate is the trace of this form. So we have some gamma mu, some for momentum, say minus m, and gamma nu q prime plus m. So both of these expressions are of this type. So the first one, in the first one, we just have m is equal to 0. So this can be written as follows. So when we open the brackets, there will be 4 terms, but the cross terms, where we have mass times the momentum, will contain the trace of 3 gamma matrices, and that's 0. So we have 2 traces, in fact, gamma mu, gamma lambda, gamma nu, gamma rho, and that's contracted with q lambda q prime rho, and then minus m squared trace gamma lambda gamma mu, gamma nu. So for these expressions, we have the ready answers. Well, I think this one is equal to 2 or is it 4? I think it's equal to 4 times the G nu G lambda G nu rho, and then summed over all pairs with with various signs. So let me see if I will be able to remember the formula correctly. So there will be the term with G mu lambda G mu rho plus G mu rho G lambda nu and minus G mu nu G lambda rho. So that's contracted with Q lambda Q prime rho. And so for this term, for sure remember that this is equal to 4 m squared G mu nu. So finally what we get is 4 times Q mu Q prime nu plus Q nu Q prime mu. So these terms, and in this term the indices are contracted, minus Q prime G mu nu and minus m squared G mu nu. So we have two tensors of this type with two indices. Yes.
Do you mind clarifying how the Q slash and the Q prime slash get outside the
So Q slash is Q lambda gamma lambda. So we just explicitly write it as the gamma matrix that sits inside that trace, and then this just numerical coefficient. So all right, then we should take the two expressions like that and multiply them, and then contract the indices Q and mu. So this gives a bunch of products of 4 vectors. So let me just write the final expression. So 1 quarter sum over the spins of m squared is then equal to 128 y squared alpha divided by p plus p prime squared, and then times a bunch of products. Let me copy them from the notes. So how do this arise? Well, we just need to contract the indices of this expression with Q being replaced by K and the one with Q replaced by P. So these two terms arise from contracting the cross terms among the two expressions. Then in the one of these expressions we also have this, and this just G mu nu just contracts the indices on the well, similar expression for the electron. So we get P prime times P. This is the coefficient which is minus mu squared. Well, it's just we use this formula in the explicit expression where we have two these tensors multiplied. Okay, so this already looks like almost an answer. What we need to do is we need to use the explicit expressions for the 4 vectors, just kinematics, plug them here, and then we'll have the formula that is the function of energy and the angle. Yes? Should be alpha squared, yes. So let's make a break for 3 minutes and I'll continue.